Welcome back. We have already studied differentiability and analyticity of complex functions and how to check analyticity using Cauchy-Riemann equations. Here we are going to discuss some properties of analytic functions. Even though infinite differentiability is the major property of analytic functions, we are skipping it as it is beyond the scope of our syllabus. Let us consider one by one. In the previous classes, we have already studied analytic functions and how to check whether a given function is analytic or not. Here we discuss some properties of analytic functions. First, we consider the property analytic function is independent of z bar. We know that if z is equal to x plus iy, then x is equal to z plus z bar by 2 and y is equal to z minus z bar divided by 2y. Let f is equal to u of xy plus I into v of xy be analytic. Suppose this is the analytic function in the complex plane. And here we can replace every x and y in terms of z and z bar using this formula, that is u of z plus z bar by 2 z minus z bar divided by 2y plus I into v of z plus z bar by 2 z minus z bar divided by 2y. That means our analytic function f is can be written as a function of z and z bar. Now we have to prove that this analytic function is independent of z bar, means if we are partially differentiating this f with respect to z bar, the answer must be 0. So to prove that f is independent of z bar, it is enough to prove that dou by dou z bar of f is equal to 0, because f can be written as a two variable function of z and z bar. So we have f is equal to u plus iv, then what is dou f by dou z bar? Dou f by dou z bar is equal to dou u by dou z bar plus I into dou v by dou z bar. Now we can write this u as a function of x and y, and these x and y are in turn functions of z and z bar. So we can apply chain rule. Then what is dou u by dou z bar? So we are partially differentiating this two variable function u with respect to the actual independent variable z and z bar. So dou u by dou z bar becomes dou u by dou x into dou x by dou z bar plus dou u by dou y into dou y by dou z bar using chain rule. So dou f by dou z bar equal to dou f by dou z bar equal to, substituting for dou u by dou z bar, dou u by dou z bar is dou u by dou x into dou x by dou z bar plus dou u by dou y into dou y by dou z bar. So this is the real part function plus I into, similarly for the variable v, again v is again a function of x and y, and these x and y are in turn functions of z and z bar. Applying the same chain rule, what is dou v by dou z bar? Dou v by dou x into dou x by dou z bar plus dou v by dou y into dou y by dou z bar. Substituting for the imaginary part, that is plus I into dou v by dou x, dou v by dou x into dou x by dou z bar plus dou v by dou y, dou v by dou y into dou y by dou z bar. Now we can substitute the values for dou x by dou z bar, because x is a function of z and z bar, dou y by dou z bar. So from our previous formula, x is equal to z plus z bar by 2. Then what is dou x by dou z bar? Dou x by dou z bar is 1 by 2, partial derivative of x with respect to z bar. And similarly, if y is equal to z minus z bar divided by 2y, then dou y by dou z bar is equal to minus 1 divided by 2i. So substituting all these values in this dou f by dou z bar is equal to dou u by dou x into dou x by dou z bar is 1 by 2 plus dou u by dou y into dou y by dou z bar, that is minus 1 by 2i plus I into dou v by dou x into dou x by dou z bar is 1 by 2 plus dou v by dou y into dou y by dou z bar minus 1 by 2i. Now expanding this bracket, that is equal to dou u by dou x into 1 by 2. Then what is minus 1 by 2i? Instead of this minus 1, we can write this as I square. So cancelling 1i, this is I by 2 plus dou u by dou y into I by 2 multiplying with this I, that is dou v by dou x into I by 2, then cancelling this I, that is minus dou v by dou y into 1 by 2. Now we are computing this dou f by dou z bar on the assumption that this f is an analytic function. If f is analytic, then we can have the Cauchy-Riemann equations. What are the Cauchy-Riemann equations? Ux is equal to Vy and Uy is equal to minus Vx. Then substituting for this Ux is equal to Vy, that is dou v by dou y into 1 by 2 plus Uy is equal to minus Vx. So this can be replaced by minus dou v by dou x into I by 2 and retaining all partial derivatives with respect to v plus dou v by dou x, this is I by 2 into I by 2 minus dou v by dou y into 1 by 2. So we can cancel the real terms, dou v by dou x into 1 by 2 minus dou v by dou x into 1 by 2, and similarly the imaginary term also get cancels, dou v by dou x into I by 2 and dou v by dou x into minus I by 2. So cancelling all these terms, so we get the answer as 0. That is dou f by dou z bar equal to 0. Dou f by dou z bar equal to 0, or we can say that if f is an analytic function, it cannot be a function of z bar, or it doesn't contain z bar. Or we can check the result. Analytic function is independent of z bar with the previous examples. F is equal to z bar and f is equal to mod z square. Mod z square can be written as z into z bar, and we have already proved that these functions are not analytic in the entire complex plane. F is equal to z bar is not analytic because it cannot satisfy Cauchy-Riemann equations. Here also it doesn't satisfy Cauchy-Riemann equation because this function is differentiable only at origin. And these two functions are not analytic and they contains z bar. If f z is analytic, for example, if we take f z is equal to z square or f z is equal to e raised to z, and we know that all these functions are analytic functions. They doesn't contain the complex conjugate part z bar. Second property, analytic function of constant absolute value is constant. So as before, we take, let f z be analytic in C. F z be analytic in the entire complex plane with the property that absolute value of this f z is constant, that is mod f z is constant, or we can say that mod f z square is equal to u square plus v square equal to some constant, say k, and we call it as equation number 1. Now differentiating this equation number 1 partially with respect to x and y respectively. Partially with respect to x and y respectively, and because this u and v are functions of x, if you are partially differentiating this equation number 1 with respect to s, what we get? Derivative of u square, that is 2u into dou u by dou x plus 2v into dou v by dou x equal to 0. Or cancelling that too, we get the equation u into ux plus v into vx is equal to 0. And similarly, if we partially differentiate the whole expression with respect to y, again we get another equation as u into uy plus v into vy equal to 0. Next, we converting all these partial derivatives in terms of u only with the help of Cauchy-Riemann equation, because we are on the assumption that f z is an analytic function. Since f z is analytic, we have the Cauchy-Riemann equations by CR equations. This ux is equal to vy and uy is equal to minus vx. So we can replace every vx and vy term in terms of u. So we have the equations ux, and what is vx? Vx is minus uy, that is minus v into uy equal to 0. Suppose this is equation number 2. And similarly, another equation uy, and what is vy? Vy is ux plus v into ux equal to 0, equation number 3. Now from these equations 2 and 3, we can eliminate the uy terms and the ux terms separately. So first we are going to eliminate uy terms from equations 2 and 3. So we are multiplying the first equation with u and the second equation with v and adding. That is equation 2 into u plus equation 3 into v implies, after that multiplication, that is u square into ux minus uv into uy equal to 0. Adding this with the third equation multiplied with v, that is uv into uy plus v square ux plus v square ux equal to 0. And adding these two equations, we get u square plus v square into ux equal to 0. Call it as equation number 4. Similarly, we can eliminate the ux term from equations 2 and 3 by multiplying also equation 2 into minus v plus equation 3 into u, that implies minus uv into ux plus v square uy equal to 0. And next a third equation with u, that is u square uy plus uv ux equal to 0. Adding these two equations, we can say that this ux term get cancels and we will left with u square plus v square into uy is equal to 0. Equation number 5. Now from equations 4 and 5, we have two different cases. Whenever this u square plus v square equal to 0, that is the constant equal to 0, or u square plus v square is not equal to 0. So you consider the first case, if this u square plus v square equal to the constant value, that is the modulus value, equal to 0, then this u is equal to 0 and v is equal to 0, because if you are adding sum of two squares, then its result equal to 0 means each of the expressions equal to 0. So u is equal to 0, v is equal to 0 implies f is equal to u plus iv, that is identically 0. And other case, that is if u square plus v square not equal to 0, that is u square plus v square equal to k, this is not equal to 0, then what are the possibilities? Then we have ux is equal to, from equation 4, ux equal to 0, 5 ui is equal to 0, ux is equal to 0 equal to ui equal to 0. And by Cauchy-Riemann equations, this ux is equal to vy is equal to uy is equal to minus vx, that is vx, that is also 0. Vx is 0. Since ux is equal to 0 and uy is equal to 0, that implies u is a constant. So u is equal to some constant, and vx is equal to vy is equal to 0 implies v is a constant. V is equal to some constant. If u and v are constant according to our assumption, then f is equal to u plus iv equal to a constant. Third property, an analytic function with a constant real part is constant. So let us take f z is equal to u plus iv. U plus iv be analytic. Suppose this is analytic in the entire complex plane with its real part constant. Real part constant means u is equal to some constant. So u is equal to constant implies its all partial derivatives with respect to x and y are zeros. So dou u by dou x equal to 0 and dou u by dou y is equal to 0. Now by Cauchy-Riemann equations, because this f z is analytic, this us is equal to vy, that is dou v by dou y is equal to 0, and uy is equal to minus vx, that is minus dou v by dou x is also 0. Since vx is equal to 0 and vy is equal to 0, what about v? Then v is also a constant. Since u and v are constant, therefore our function, the analytic function f z is equal to u plus iv is equal to a constant plus I into another constant, that is a new constant. So this is constant. And similarly we can prove that if f is an analytic function with the imaginary part is constant, then using the same pattern we can show that f z is equal to u plus iv becomes a constant. Fourth property, an analytic function with the constant argument is constant. Let f z is equal to u plus iv be analytic in C with its argument. With the argument of f z, arg f z is a constant, say some constant. Okay. What is argument of f z? If f z is equal to u plus iv, then argument of f z is tan inverse v by u is a constant. Tan inverse v by u constant means v by u constant, or we can take u by v equal to some constant, say k. So that implies u minus vk is equal to 0. Question number 1. Now to prove that an analytic function with a constant argument is constant, we are considering a constant multiple 1 plus ik into f z. And simplifying this expression, 1 plus ik into f z equal to 1 plus ik into u plus iv. So using the multiplication rule, this is product of the real part minus product of the imaginary part u minus vk, that is the real part of this product, plus I into collecting all imaginary part, that is v plus uk. Now from equation number 1, what is the value of u minus vk? This u minus vk is equal to 0. So that is 0 plus I into v plus uk. That is a new complex number, or the complex function 1 plus ik into f z is an analytic function having its real part is fixed or real part is constant. Since real part of 1 plus ik into f z is constant, since the real part is constant, according to our previous result, the analytic function is constant. We have 1 plus ik into f z is a constant. So 1 plus ik into f z is a constant means that is a constant multiple of f z. So f z is also a constant. Fifth property, if f z is equal to u plus iv is analytic, then u is equal to constant and v is equal to constant are families of curves cutting orthogonally. Curves cutting orthogonally means if we draw the tangent at their point of intersection, their tangents are perpendicular to each other, and we are checking the perpendicularity condition for two straight lines. So it is given that this u means u is a function of x and y, u is equal to some constant, say c1. Therefore, it's a differential, that is du is equal to 0. So we have dou u by dou x into dx plus dou u by dou y into dy equal to 0. Therefore, what is dy by dx? Therefore, dy by dx is equal to minus dou u by dou x divided by dou u by dou y, that is minus ux divided by uy. Now in the family of curves, u is equal to a constant, say c1, dy by dx is its instantaneous slope. Let us take this slope as m1. Let m1 be the slope of the tangent. Slope of the tangent to the curve u is equal to c1, that is m1 is equal to minus ux divided by uy, equation number 1. Similarly, consider the another family of curves, say v is equal to a constant, that is v of xy is equal to c2. Therefore, dv is equal to 0. So the total derivative dou v by dou x into dx plus dou v by dou y into dy is equal to 0. So from which we can find the value of dy by dx on the second family of curve, dy by dx as minus dou v by dou x, that is minus vx divided by vy. If m2 is the slope of the tangent to the family of curve v is equal to c2, if m2 is the slope of the tangent to the curve, say v is equal to c2, then m2 is equal to, what is m2? m2 is minus vx divided by vy. Therefore, product of the slopes for my m1 m2 is equal to minus ux divided by uy into minus vx divided by vy. Now since f is analytic, we can apply the Cauchy-Riemann equations. What is ux? Ux is equal to vy, that is minus vy divided by uy into minus vx is uy is equal to minus vx divided by vy, or this product is equal to minus 1. As an example, we can see that we know f is equal to z, or x plus iy is an analytic function with a real part. What is the real part? So this is equal to in the form u plus iv. So the real part is u is equal to x and imaginary part v is equal to y. Now what are the families of curves? U is a constant. So u is equal to c1 implies x is equal to c1, and v is equal to c2 implies the function y is equal to c2. So what are the natures of the families of curves? X is equal to c1 and y is equal to c2. See, x is equal to c1 means all vertical lines, and y is equal to c2 means all horizontal lines. For example, x is equal to c1. So x is equal to c1 means x is equal to 1. Then we have the vertical line, and y is equal to, suppose c2 is 1, then y is equal to 1. Another line. So these lines are cutting orthogonally. So this is true for any values of the parameters c1 and c2. So that is a generalized result. If f is an analytic function, the families of curves u is a constant and v is a constant are cutting orthogonally. That is a very important property.